guys. Alright, another batch reactor problem. Here we go. Looks so scary. But it's not. Kind of scary. No, it's not. Anyway, so what we want to do here is we want to organize the problem. And like always, my strategy has always been, and I'm going to use highlighter in this one. It kind of makes it easier. Find out what type of reactor and what are the conditions, right? This is very important to do the mass balance and material balance correctly. Okay, so moving forward. So what type of reactor? Batch reactor. What are the conditions? I'll do it in blue. It's well mixed, which means the concentration everywhere inside of the batch reactor is going to be the same. Okay? And the second one is isothermal, which is good. Okay, so that means all the rate constants are going to be constant. Rate constants are constants. Okay, so going forth from here, well, what do we want to do? Well, let's organize information and then we'll begin our material balance. Okay, so we know that we got a weird rate reaction, which is going to make the calculus different later, but you got one rate constant times Ca over 1 plus K2 Ca. Now, as I said in rates of reaction videos, you have first order, second order, third order, and etc. But you can also have weird ones too. You can have stuff that's all, numerators, denominators. They can get more crazier than this. Maybe I do this. I don't know. But for this problem, you got this. Okay? So then let's write the information we got for the rate of reaction there. We got K1 is equal to 5, K2 is equal to 4. And the units of the rate constants are in hours. So let's keep that in mind if we see things in minutes and seconds later on, which most likely seconds, that we can convert and do our dimensional analysis to make this thing work. Okay, second thing. Okay, so we have a batch reactor. So let's start up on the material balance, right? So we have our box. I always like to draw it and get a visual on it. Then we have everything inside of here. Okay, so you have in minus out plus generation. Remember, the consumption term is a part of generation. We just flip it to a negative sign if things are being consumed. In this case, A will be consumed, and you'll see how that works later. Okay, but nothing goes in, and nothing comes out while the time is counting inside that box. Because you can imagine it has a lid. You can't take things in or out. Okay, so the generation term is equal to RA times V. And it's not dV because you don't have different concentrations everywhere inside the reactor. We're going to use big V. Okay? So dNA over dt. Now, in previous videos, I showed you how to divide V to the other side, but in short, we got it for time purposes. This is what it means. You divide V to the other side like this, cancel this out, and a V folds in here. It gives you concentration, leaving you with this. This is your equation to work with at this point. Okay, so let's plug in the rate of reaction. Right? And now we have negative RA. That sign is super important. It'll screw up all your results if you don't have that right. So put that negative sign to the right side for right here, right? For this equation. And what you're going to get is you're going to get negative K1Ca over 1 plus K2Ca, right? Equal to dCa over dt. Okay, guys, we're almost there. We're doing good. All right. So what are they giving us in the problem, right? They tell us calculate the time in hours. So we're going to be aiming for time. Okay? So how about this? How about we move the time to one side of the equation? Right? So we can do negative K1 Ca for 1 plus K2 Ca d of t equal to dCa. Okay. So what can we do here? Now let's move the Ca's to the other side, right? dt is going to equal to 1 plus K2 Ca in parentheses over K1 Ca. I'll leave the negative sign over here so we don't confuse ourselves. We can always move that over later. Okay, so let's find out what our initial concentrations and final concentrations are, because if you're solving for the time, you're going to have that kind of information. So I'll use the highlighter. You want a result in 2 moles, so that's your final. Right? So what's your initial? Initially, there are 4 moles of A. Okay? 4 and 2. That's basically what it is. So then we could say Ca naught is equal to 4 moles. Then we could say Ca at some other time later is equal to 2 moles. Okay, we're good. We can do integration at this point. So if we do negative from 0 to time of d of t, right? And over here, we want to do this calculation. There we go. dCA. So I'm going to move a little faster because it's going to be an integral that's going to take a minute. Okay, but let's go from CAO to CA1. And remember that time when I said you can move the negative sign later? Basically this guy and this guy. Well, let's do that now. Let's flip these bounds and remove it, right? So now you're going to have time is going to be equal to the integral of CA1, which is going to be 2, to CAO, which is 4, right? 1 plus K2 CA over K1 CA, right? Now, I'd like to add in at this point, I'm going to add in my K's, right? So what were those values? We had them up here. 5 and 4, okay? And those are in terms of hours. So we know our time is going to come out in terms of hours. So that's the takeaway from that. Okay, so let's do this. Time is equal to the integral of CA1, which is 2, 4, 1 plus 4CA, because that's for K2, over 5 of CA, dCA. There we go. Okay, guys, we're nearly there. I'm excited. So I could do many things here. I could pull the fifth out, all that stuff. I'm actually going to do that. All right. So let's pull out 1/5 out here. Let's have 1 plus 4CA over CA. And that gives me dCA. Now I can split this up into two integrals, right? Using the denominator. So I have dCA over CA from 2 to 4, right? And that's going to be plus integral of 4 dCA. Reason why is because the CA here and the CA here will cancel when you do that division, okay? And that made, and of course, 2 to 4. Okay, a little easier than I thought it'd be. That's good. Okay, so now we want to do the ln of CA, which would be the ln of 4 over 2, right? Doing that first integral. Second integral is going to be 4 times 4 minus 2, right? And then we got this. So now time is going to equal to 1/5 ln of 2 plus 8. Okay? 1/5 on the outside. Now t is equal to 1/5 time. Okay, I'll just do this in the calculator at this point. Right? So the time that we're waiting for, let's go to MATLAB. I have it in matrix mode. I'm very excited to show you guys. Yeah. Okay. So 1 divided by 5 times the natural log. In MATLAB, it's just log, right? So of 2, right? And I'm going to add to that. Is it add? Make sure. Yeah, plus 8. Plus 8, and there we go. So what do we... I did something weird. Oh, extra parentheses. My bad. Nope. Oh, I see. I see. Also, in MATLAB, you can't just do this. You got to put the multiplication sign in. It's not very smart. Okay, 1.7386. And that's going to be in terms of hours. Now, for this class, it's been a royal pain dealing with decimal places, but they always tell you at the end of the problem usually how many decimals. 2 decimal places. So your answer in terms of hours is going to be 1.74 hours. Okay, guys, I hope this one helped. It was a little different. This time you're solving for time. Usually you have the time, you're solving for concentration, but this is it's flipped over. So I hope that helped, and I hope it helps you on your exam. I'll be doing more problems with different types of reactors in future videos. Please leave comments, anything I may have messed up on, or anything you want clarification on. Alright, guys, stay tuned, and hope that helped.